What is up? What's going on? Welcome back to Building Stuff with Nova. I'm your host, Dr. Nee, and as you can see, I'm not behind my desk today. I'm not in front of a computer by typical measures. I am right here, IRL. I'm in real life. I am at a laboratory today. This is our second in the field lab, and today I am at MIT, the MIT Plasma Science and Fusion Center. That's right. And for those who don't know, again, let me remind you, this is Building Stuff with Nova. This is what we call our virtual laboratory, your ideation laboratory, your mastermind. This place where we build together. And so I want to know who's in the chat. Even though we're not live, we have the team in the chat. So let us know where you're joining us from. Let us know what you're doing. We want to take you on a journey through this Fusion Center and show you some really cool stuff. So stay with us today. Feel free to ask questions. Feel free to let us know what you think about what you're going to see, because I promise you, you're going to see something that's going to literally blow your mind. As I'm walking through the entrance of the center, you can see some of the pictures on the wall here of all the cool research that's going on here. And I can't wait to ask questions, because we've talked a little bit about fusion already on the channel, and we're going to get some real life experts, researchers that are working in the field today as we speak, and they're going to break things down for us. As I am coming into the laboratory, I see over here to my right two wonderful students, Audrey and Will. How y'all doing today?
Very good. How are you?
You doing all right?
Good.
All right, good. So they're joining me today. They're going to be our tour guides. I'm going to be your personal guide too. But I want you to know that you can ask questions. As I've already said, we have our team in the chat. So feel free to ask questions. Feel free to let us know what you think. And we're going to have a good time. So first and foremost, can you let the people know, more importantly, who you are, what do you do, why are you here with us today?
Yeah, hi, I'm Audrey Saltzman. I am a fourth-year graduate student at MIT in nuclear science and engineering. And I study fusion energy and using plasma physics to try to predict its behavior.
Got it. And Will?
I'm Will. I'm also a NSC PhD student. I'm going into my second year, so just getting acquainted with this field, but I also work on trying to make fusion energy a real source of energy in the world, and hopefully a clean source of energy that makes the world a better place. So I also do research on the parts of the thing that you're standing in front of.
Oh, let's see, they're already looking at the thing I'm standing in front of. Show some love to Audrey and Will in the chat, by the way. And they're going to tell us really quick. All right, before we go in, this is this awesome picture that we're standing in front of. Will, since you brought it up, like, what is this? What am I looking at right here?
This is Alcator C-Mod. This is a research reactor that was built here at MIT a number of decades ago at this point. It's what's called a tokamak. It creates plasmas and through a variety of means.
So this is a place basically where fusion can take place, like within this.
That's correct. Yes.
All right, and is this the real size, or is it scaled up, or is it a little smaller? How does this relate to what the actual size of the reactor looks like?
So this is relatively close. This is a port here that unfortunate grad students used to have to crawl through.
Oh, that's the entrance and how you would get in and out
yes,
of it? Okay.
Yes. So fisheye, this part is probably a little bit bigger. This is a little bit smaller.
Okay, got it. So fisheye lens, that's the photo.
Yeah.
I love that you have this, because I think I understand that this isn't physically in place anymore. Like, you all have taken this down, taken it apart?
Correct.
All right, why? Why are you taking it apart?
We took it apart so we could have room for new experiments. So we stopped operating this device in 2016, and we're now going to be building new experiments in this room.
Oh, so we're about to update it. We're going to get the new and improved version.
It's not going to be a tokamak.
Not going to be a tokamak, but it's going to be another type of reactor where fusion energy can take place?
I think it's just going to be an experiment for the sake of fusion.
Ah, for the sake of fusion.
No fusion.
Oh, okay. Well,
Okay.
you all keep that in mind. We're going to be looking at different things that I guess are components of the different types of experiments that happen as it relates to fusion energy research. But again, one more time for this, when you said that this is a big reactor, it's like obviously it looks pretty circular. Are we saying that there would be plasma, Will, that's like going around this as a circle?
Yes,
tokamak?
exactly. It's there's some pictures around here, but yeah, it'll go around. The characteristic of a tokamak is that your plasma follows along magnetic field lines around this donut shape.
Right.
And that's what's confining
And so these coils here that we see on the outside, or maybe even on the inside too, is creating a way to trap the plasma in the middle with the magnetism.
So I don't think you can see it in this, but surrounding this donut shape are magnetic coils. They're
Okay.
often shaped like a D.
So, okay, so this is not it. This is not the coils. This is
No, so that's something that I personally work on within my group. Those are radio frequency antennas. So that's a way to, once you've created a plasma, actually pump in enough energy such that fusion can actually occur. So you're heating the plasma, just like your cell phone has waves that get sent out in and out, and these are just really powerful antennas, basically.
Got it.
But the actual way that you're confining the plasma is through the magnetic fields. There are ones that are, like I said, D-shaped. Those are the toroidal coils, and then there's poloidal coils that kind of are shaped like a circle below and above the
And
reactor.
there's magnetic coils inside of this, but you can't see
As
them.
well, yeah, that's the solenoid.
All right, magnetic coils. I'm gonna give a shout out. You know how we do here on the channel. Nova in the chat. Go ahead and drop a few definitions for us because they've been saying a lot, and I want to make sure that they stay with us. So magnetic coils create an electromagnetic field that allows the plasma to basically stay contained in the tokamak. Tokamak is a type of fusion reactor, right? That y'all are not necessarily using this one anymore, but it's a type of fusion reactor. And this one, ladies and gentlemen, was called the Alcator C-Mod. The Alcator C-Mod, that was the name of this one, right? Mm-hmm. All right, cool. All right, well, let's keep it going. We want to get to see some actual physical examples. Let's head over here. I'm just telling y'all where to go in your own lab. I don't know where are we headed right now.
We are gonna head to our design center.
So this is the design center.
Yes.
All right. I think I've worked in a design center before. If it looks like this, looks pretty cool. This is where a lot of brilliant minds go to work, I see. Awesome. Will, let me ask you a quick question real quick. As I'm walking ahead and I see something, it definitely looks like something I've seen in Hollywood before. What's this straight ahead in front of me?
Yeah, so this is what we would call like the control room for what was Alcator C-Mod. On this board, you've got lots of lights and signals that show, for example, like the amount of current that you're putting through the magnetic coils that we just talked about, how good your vacuum is, temperatures of lots of different things.
Yeah.
And so this is how you'd be able to visually see what's going on with your reactor, the health of your reactor. If something's going wrong, like as you mentioned movies, maybe all of these lights would be flashing.
Yeah, I mean, I feel like in a movie, they'd be like, hey, get in here now. The numbers are going crazy. They're spiking it. Yeah. But this was basically, like you said, the control panel for that tokamak that we saw in the picture.
Yeah.
Absolutely.
All right. And this was not only for that one, but I guess all the other tokamaks or a few others that came before it. Because Alcator C-Mod, is that like one of a series, or how is that?
Yeah, this is one of a series. This was only the control panel for Alcator C-Mod. The previous devices were actually in a different building.
Got it. Can I get a closer look though? Because this looks like some, I mean, you said it's older technology, right?
Yeah.
So, all right, this does look a bit antiquated, and I see all like the LED screens and everything.
This would have been state of the art about 25 years ago.
Okay.
Or maybe 35 years ago.
35 years ago. Wow, this was the original, the OG. That's why I knew I saw it in the movie, chat. I knew I saw it in the movie. And then we got like the little Wizard of Oz.
Yes, so you can actually see the technology that
the
is
brains,
would be for running this.
Look at the brains. Hey, chat, this reminds me of something that we're trying to do for our escape room. Y'all see that? This is real stuff. Like, so this is all of the circuitry that goes to control this command center, right? And are we only like reading things from the tokamak, or does this supply power somehow to it as well?
This isn't power. This is the control system.
Okay, got it. I love it. I love that y'all keeping it in the design center as well. There's a lot of inspiration that just comes from seeing the history here. All right. No, let's keep it open. So that's real nice. I don't know if that's what they want to keep exposed. All right. So what else happens in here? I see this big. I don't know, what is this? Like a big screw?
Yeah, so that was a screw that was used for Alcator C-Mod to hold the lid on.
This is it was made into like a nice little presentation here in chat. Come take a look at this. It's an alloy 718. Remember we were talking about, for those who remember watching when we had Jay Flores on and we were talking about different types of alloys. But this is an alloy 718 drawbar for the Alcatar. Drawbar, what does that mean? What is that? Is that
Screw.
like screw? Oh,
I guess.
Drawbar means screw presented. Okay. So this was basically preserved to be like a
so
memento.
there's a funny story behind this, actually.
Oh, really?
So this was given as a present to someone who was important in the Alcator C-Mod project.
Uh-huh.
And they put this together, made it look nice, and brought it to his house. And this is a bit heavy. You can try picking it up in a second if you want.
Oh, listen, I can pick this up easy. I don't know. I don't know if I want to do it on camera. Let me just.
Need some help?
I didn't try yet. Yeah, Will, let's pick it up together.
Ready?
Yeah.
All right.
Will, do your side.
Gotcha.
Okay. I thought it was all me. Felt like it was all me for a second there. Okay.
All right.
All right. So someone gave this somebody as a gift.
Yes, and they brought it to their new home with
Sounds like a prank to me. If you
brand new wood floors, and they cracked the brand new wood floors. So the person unrequested the gift, and it got sent back here, which is why we have it.
They unrequested the gift, chat. Let me know in the chat right now if someone gave you this and it became a liability to your new floors. Would you unrequest it, or would you hang on to it? I don't know. Apparently, the person wasn't all that grateful, if you ask me. But if you want to get it off your hands, I can take it back to North Carolina. If you want.
You can see if you want to do the paperwork for that one.
I wonder how much of a carry-on fee they're gonna charge me for something. This is definitely over 50 pounds. I promise you that. Yeah. Okay, this is cool. So this was a screw. What did it do on the tokamak, on the Alcator?
So there was a lid on top of the tokamak that held together the entire device. So there was like around 50 of these or so that were used to hold this lid on under really, really strong forces that are occurring in this device and actually hold it together.
Man, so if this was like one of the screws to hold it together, you can only imagine what type of forces we were dealing with. And did people have to physically take this on and off? I mean, we could barely pick it up. That seems like a tough job right there.
There is a crane in that room. I don't know if they specifically used it for the screws.
Okay, cool. All right, well, hey, we got to figure out how to get this back to North Carolina, but we'll do that offline. So what else we got? What's here on your feet? I see some other like demonstrations y'all have here.
Yeah, this is what we call the linear plasma demo.
The linear plasma demo. Okay.
We can talk about reactors and plasmas, but it's a lot cooler to see things actually in person. So if Audrey can turn the device on.
Whoa, come on. Audrey, you just turned it on just kind of flippantly.
Yeah,
like, I don't know. I've never been around
Okay. So right now, that sound that the mic may or may not be picking up is a vacuum pump. So we're pumping down this chamber here.
Yeah.
And that's just because plasmas are a lot easier to create when there's not a lot of gases being, or a lot of vacuum.
So Mike, what you're saying is that sound, to me, it sounds like a bunch of like, I don't know, danger. But what you're saying is it's basically just removing air from inside of this tube?
That's correct, yes.
Okay, creating a vacuum. All right, so it's creating a vacuum because this plasma is more easily produced in that type of environment?
So it's a combination of having not a lot of air in this chamber, and then also what we're doing is applying a very strong electric field or voltage between these two circular or spherical electrodes.
Here at the end. All right, so I don't know if you all can see that, chat, but at the end, as you said, spherical, there's like two balls on each side that are like pushing out a current between each other.
Yeah, exactly. So there's a cathode and an anode.
Okay.
I'm not sure which one's which on this, but and that's ionizing the gases in here and creating a plasma.
So what is plasma? So here's the thing, like when I was in school, and I don't know if you all remember this, it was like, what are the 3 states of matter? That's what they would say. They would say solid, liquid, gas, until I got older and realized I had been lied to. There are not just 3 states of matter. And one of the states that they never mentioned when I was learning this in school is plasma. What exactly is plasma? I mean, we see the nice little pretty, it looks like a lightsaber going through here. Like, what is plasma exactly?
So with atoms, whether it be solid, liquid, or gas, you have a nucleus, and then you have electrons that are surrounding the nucleus. And if you put enough energy into the system, you can actually rip those electrons off of the of the nucleus and basically allow them to flow freely among a medium.
Okay. And that medium is gas in this case.
In this case, it's gas. Yeah,
Okay.
it's a lot easier to do that with gases. And so you have electrons that are just flying around, and that's what allows the current to pass through them.
Got it, got it. So this isn't fusion itself. This is just plasma.
Yes.
But plasma is, how does it relate to fusion? Like, what does plasma got to do with fusion?
To get fusion to work, you have to get it to really, really high energies, and one way to do that is to heat it up a lot, and when you heat things up, a gas up a lot, it turns into plasma. So we are stuck working with plasma if we want fusion to happen.
Got it. So it's like a component of what's necessary for fusion.
Yes.
I love it. Chat, that's a good point. Take a beat on really quick and ask a few questions, because I have some questions, probably some basic ones. So don't be afraid to ask whatever they are. Hopefully we got Nova in the chat. You know, we always have Nova in the chat, and we have the team in the chat to answer any questions you have. But I'm gonna ask my basic question. You ready? Why is it so cute and pink? Why we can't get like a, you know, dark charcoal type color? You know, something blue or something. Like, why is it pink?
Well, if you paid attention, when we first turned it on, it was actually purple.
Oh, okay. Then it got lighter.
Yeah.
Okay.
Yeah. So what this is nitrogen plasma.
Mm-hmm.
So nitrogen, when you turn it into plasma, glows this pink color. And since this is air, which is predominantly nitrogen, we get the pink color.
Oh, okay. So it's nitrogen plasma, not because you're putting nitrogen in there. It's just naturally a nitrogen that makes up the air that's in there.
Yep.
And then when you heat it up, is this hot?
Nope.
I don't know. You did that. I don't know. With her touching it, it still doesn't. Will, you touch it. You touch it.
Yeah.
Okay. All right. I guess I can touch it now. Okay. No, I'm good. So Audrey, there's a glass around this right now, though, right?
Mm-hmm.
So that's how it's contained.
Yes.
Can I touch plasma? Another basic question. Chat, don't be afraid. Can I touch plasma like with my hand in real life? I don't like. Probably shouldn't, right? Don't try this at home. I'm just asking questions. We're on this. I'm a structural engineer, remember?
It probably wouldn't be so good for your
Okay, all right. That's enough. That's enough to know that we shouldn't try. I'm just curious because, like, I know heat is involved, and we tried to break this down a little bit for you all. But in producing this plasma, you got a lot of heat. In this case, you have an electrical current. Obviously, you need to contain the plasma. So in this case, you're containing it with glass. Is that the only way that you can basically, like, keep plasma or where you need it to be, or?
No. So what I'll do is flip this thing on.
Yeah, just turn the stuff on. Okay.
And in a second, it'll turn on these coils. And so what we're doing is creating a magnetic field around these coils. And that's very similar to what happens in a tokamak reactor. You're confining the plasma with a strong magnetic field, and that's what's happening here.
So I don't know if they can see it, right? I want to make sure they can see it. Shout out to Joni behind the camera. You all say, hey, Joni in the chat. Joni's behind the camera. Joni, I don't know if they can see this, but it's almost like turning into like a dog bone type of thing because it's wider over here, but then because you turn this on, these coils are now experiencing a current.
That's true, yeah. So you have a current flowing through the coils.
Through here, okay.
And it's creating a magnetic field that's basically squeezing the plasma.
That's crazy. Yeah. So it's like squeezing it. So in the middle of this linear plasma tube, I guess, linear plasma tube is getting more narrow. The diameter is decreasing because there is a magnetic field now that's squishing it. This is dope. So like instead of trying to physically contain it with glass, you're looking at the way to contain it with a magnetic field going through the coil.
Exactly.
So you don't have to touch it with your hands.
Exactly.
Like I was just talking about a second ago.
Yeah, and we have an even more powerful magnet here if you want to try that.
So this is a magnet.
Yes.
So what is this going to do?
Why don't you find out?
Hold on, see. I don't know if this is a setup or not. So this is a magnet, and this is make sure that the people at home can know that this is a real magnet. Look at that. You see the paper clips sticking to it? That's pretty powerful. All right. And I'm guessing, Audrey, you said, why don't you find out? I'm guessing that when I move this underneath it, something safe is going to happen first and foremost.
Yes.
But the plasma
Just let me go stand over there.
Oh, man, see, you're trying to set me up here. All right, should I go like here?
Yeah.
All right. Yo.
And you can twist it back and forth.
So I'm bending the plasma. Do y'all see that? Chat, do you see that? That is neat. So I'm basically, is it repelling it or is it like, I'm trying to figure out. So the same thing that's basically happening here where it's squeezing the plasma magnetically. This right here, the magnet that is this physical magnet here, is manipulating how the plasma is running through the center of the tube. That's pretty cool.
Yeah, so that's about a 1 Tesla magnet. Tesla is the unit we use to measure how strong magnetic fields are.
Yeah.
And the magnets that we use for actually building tokamaks, the tokamaks we're designing today are between 10 and 20 Tesla.
10 and 20 Tesla.
So 10 to 20 times stronger than that magnet. That's moving the plasma around.
Than this magnet.
Yes.
All right. I'm gonna try to break this down. Don't forget to drop your questions in the chat, because I am on this journey with you. This is pretty cool. So basically, if I move along the side of this, I'll continue to see the plasma. And this is almost creating a circular version of what this is doing. Is that basically what's happening? So like this coil, the magnetic field that's coming from this coil, or that's being produced by that wire, is similar to what's happening here, but only this is going around it. But this is sort of, is that a cool way of explaining it?
Well, so the magnetic fields for the magnet is going across here, so it's pointed in one way or another.
Okay, got it.
And you might have some it extending over or under.
Because of how strong it is.
Exactly.
How strong we are.
Yeah.
Okay. Cool.
And then with these, a current along these coils will produce a field that's going through or through this way or through that way.
Oh, okay. Got it.
So along the length of the tube.
I need to see some love in the chat. Again, we're not live, but when I see you all see this, I need to see some emotes, drop some love, let everybody know. Please let Will and Audrey know that this is dope. I love this demonstration. And so this gives you sort of a basic understanding of how magnets or magnetism allows you to manipulate plasma that's inside of a tube or inside of this bottle.
Exactly. Yeah.
All right, dope. Let's get the love going. Really quick, I just noticed this before we move on. Are these basically like real life versions of plasma? Like how we see plasma in real life?
Exactly. It's not just in reactors, it's in a lot of places, and stars and lightning.
Lightning is plasma.
It is, yeah. It's that strong electrical current is ionizing the gas in our atmosphere and creating plasma.
I feel like this is a lab that is kind of like where superpowers could come from. Like, I don't know, this is what I feel like. I watch a lot of comic books and everything, but we can keep going. I think there's a question, and shout out to Kaja. We got the team here. Kaja, what was the question you want to throw in?
If lasers are plasma, how can you touch them?
Oh, these
without it
lasers down
burning your
here.
hand if you can't touch the plasma in there?
So lasers aren't a plasma themselves, but they can be used to create plasmas. And so just as we mentioned tokamaks and reactors of that kind, there are other ways of making plasmas. And another example of that would be the National Ignition Facility in California. And they use really, really powerful lasers to basically obliterate a structure and create a plasma that way. So there's a variety of different ways to make one.
Dope. Thanks for the question. And by the way, that was Will's brilliant answer to the question of if lasers are plasma, how come we can touch them? He just said, you heard it, just rewind, VOD, you all can check that out. It is not plasma, it can use to create plasma.
Yep.
Lasers. Okay, cool, what else we got? I'm ready to see what else we got here. I see you all's shirts here. Y'all both have on a similar shirt. It's not Alcator, like we talked about, Alcator, which is what's the tokamak, and I think this is a picture of it here, Alcator on the bottom. Y'all have a shirt that says Alcator.
Yes.
Alcator. What does that mean?
It means Student Tabletop Taurus.
Okay, not an acronym. That's not an acronym for that, is it?
Italian.
Oh, really? Okay, cool. Well, let's go see what the Alcator has to offer us here. Okay, go ahead. Hope y'all are enjoying this chat, enjoying this tour, our second IRL virtual field trip tour. Now we're going into a dark room. Okay, the light is on now. I feel good. All right, what do we got? What do we have? This is a pretty cool lab. This reminds me of grad school. That's what this smell reminds me of. I'll tell you that. That's for sure. What do we got?
So right now we're in the nuclear makerspace, which is a space for nuclear science and engineering students as well as physics students at MIT and the PSFC to create things. And one of those things that a group of students have made is this demo
Donut.
called Alcator.
Alcator. Oh, so this is Alcator.
This is, yes.
So this is a donut version of what we just saw a second ago.
In a lot of ways, yes.
In a lot of ways. Okay, cool. Alcator. All right. So that's what the name. And you said it's a student tabletop. What's the other way you refer?
Taurus.
Taurus. Okay. Awesome. Do
Yeah,
not
this
touch.
is one of the only nuclear makerspaces in the country. This is an example of MIT really like getting hands-on and letting students mess
Yo.
with things.
I'm sorry for the clapping. I'm excited, Audrey. So chat, we've always referred to this as a virtual makerspace. Now you are on a virtual field trip and I'm in a real makerspace, but not just any makerspace, a nuclear makerspace. Get a load of this. Shout out to MIT for allowing us to be here. All right, so in this place, we're able to do something similar. Is this like another one of those, I guess, vacuum pumps?
Yeah.
Right? I'm learning, right? Okay, cool.
Do you want to hit the
You want
on
me to hit
switch?
it? See, I'm just gonna trust you. I'm just trusting you with a whole lot. So just hit this one.
Yep.
All right. So let me explain to y'all what's happening here, right? Based on the lesson I just got 5 minutes ago. This is removing the air from the center of the Alcator, making it a vacuum. Okay, cool. I might need some kind of credentials when I leave here. All right, so we got a vacuum that's being created in the middle of this Alcator, and the whole purpose of this, since students made this, was to see if there's a way to, I guess, create a circular plasma containment.
We wanted to get to show you plasma and how it looks in a device like the ones we're studying.
So you're part of the people who came up with it, Audrey.
Yes.
So y'all were just kind of like, hey, spitballing one day and said, let's see if we can manipulate this further. Give me the backstory just a little bit since you were part of it.
Yes, I'm just opening the vacuum here. Now
Okay.
it's on.
Oh, okay. Those numbers? Okay. I see coils going around it, so we also have a little bit of a magnetism or a magnetic field that we can create. So what's the backstory? Give me the backstory really quick, Audrey.
Yeah, the backstory to this, there were around 12 grad students my year, when we were first year grad students in all of our classes studying plasma physics. We were doing so many things on paper and in theory, and we wanted to actually get a hands-on experience with plasmas. There isn't an experiment here anymore. Alcator C-Mod was shut down in 2016, so we decided to build our own. And we wanted to build something that could be used to show what plasma is to the world.
Got it. So this is almost like a scaled down version of what would be happening inside of a tokamak.
Mm-hmm.
The plasma inside of a tokamak will be behaving similar to what we're about to see here.
Exactly, yes.
So right now, how is this different? Because you told me that it was electrical current going between those two little balls on the linear one. I don't see those balls in this. So how is the environment being created, or how's the plasma being created in this case, Will?
Yeah, so like I said, there's a lot of different ways of making a plasma. And in this particular example, instead of magnetic fields, we're sending radio frequency waves into the plasma. And as I showed you with the diagram of Alcator C-Mod, you have an antenna. These coils around the device is basically just another way of making an antenna. And
okay.
We send a wave into the plasma, or into the gas in this point. It basically jiggles around some particles, and those jiggled particles will collide with other particles, and that's how you basically heat up the gas such that it can make a plasma.
Okay. Now I have a couple of questions.
Sure.
All right. So you said something about jiggling around particles. Hold the jiggle around particles just a little bit, Audrey. I'm gonna be back to that. But in terms of this, the waves, you said you're sending waves to it. So it was electrical current over here. What type of waves? Are we talking about like microwaves? Or like what type of waves?
So these are radio frequency waves. So
Like FM.
Exactly, yeah, FM, AM. We have a particular frequency that
Okay.
we use for this, and it works by, like I said, creating oscillations in the particles. In this case, the frequency that we want is in the radio frequency band, so to speak.
So those radio waves also create an environment for plasma to be created.
Exactly.
basically.
Yeah, so it's kind of exactly like your microwave, except for the waves here are about 22 meters long,
Okay.
and the waves in a microwave are about 1 millimeter.
Got it. Got it. I love it. I love it. So, all right, never mind. My mind's going everywhere. Here's another question before I get to the particles. When we're over there, y'all said just put your hand on it, I touched and everything. Why do we have? Why is this one in solitary confinement right now? Like, what's going on?
There's a nice do not touch sign.
Oh,
there.
okay. I didn't touch it. You on it? I didn't touch it. All right. So.
It's not on yet. You'll be
Okay.
fine.
All right. So no, why is this one in a cage and the other one's not? Like, what's the difference?
Well, there's two reasons. This acrylic shield is for protecting us in case this very delicate glass container has an issue with something
Explodes?
in place. It might
Okay,
explode,
all right.
implode. So that
Technical
would just protect us in that case.
Okay.
In addition, there are these metal wires that are surrounding the device.
Okay.
And that's creating something called a Faraday cage,
Mm-hmm.
such that the waves that we are sending into the plasma, they may be reflected or absorbed at different points, and this is just to protect us from absorbing those waves ourselves.
So basically, because you're using waves in this case, it could possibly leak out, or if it gets
Exactly,
out,
yeah.
it's more hazardous.
Yeah, we don't want to get cooked.
We don't want to get cooked. Yeah, I don't like going in the
we want
microwave.
the plasma to get cooked. We don't want ours.
Right,
to get
keep it to the
cooked.
plasma. All right, I got it. And this is taking a lot longer. Is that simply because of the volume or the space within this tube is greater than over there?
Well,
Or-
so I think we're ready to go. The vacuum gauge is.
Oh, we're good.
stopped
Okay, I
working,
thought
so
I
that's
didn't see
usually when we
anything.
start,
I thought it was nothing
No,
happening right.
We
Okay.
have to turn the power on.
Yeah.
Oh, okay. So where are we ready to?
Yep. So what Will is going to do here is he is going to turn on the power to our antenna. He is looking at the dial and he has it seeing how much power is going into it. And now he can increase the power.
Okay. Will, why you have a napkin in your hand? Does that have anything to do with it?
This is creating the waves that we're sending
Oh,
into the
okay. So
plasma.
it's a buffer.
Sometimes it gets a little bit shocky.
Okay,
and,
okay.
The paper towel helps. So
Okay,
that
got
you
you.
get a little shock.
Yeah, so it looks like you're starting to get a plasma there. Maybe we can turn it up a little bit more.
Nice and
And
purplish.
we can turn the light off.
Oh, you're ready. When the light goes off, the party starts. Go ahead.
Are you good, Will?
Ooh. Look at the plasma.
So this is another nitrogen plasma, and this time in a circle, and this time made with radio waves.
Wow. Wow. It just really looks like hot gas, really. Like, that's pretty much what plasma is. So I don't
That's
know
what
how
it
it looks
is.
to you all, chat, on the stream. And please go ahead and drop your admiration, because we got the team in the chat checking it out with you. But this is basically plasma made into a circle. It looks like, pink, purplish gas, and it's hot, right? Like, what's the temperature of the inside?
So plasmas are weird. Remember how we said that the electrons are separate from the nuclei?
Uh-huh.
So because they're not together, they actually have different temperatures.
Ah,
And
okay.
so in this case, the electrons are about 11,000 degrees Kelvin.
Wow.
And the ions in gas, so the atoms, those are about room temperature, a little warmer.
Mm-hmm. The 999, what's that number up there indicate?
That means our pressure gauge has maxed out and we're at a low enough pressure it can't tell us what pressure it is.
Okay.
So that's supposed to be reading in millitorr.
Millitorr.
Yes.
What's millitorr? I'm sorry, I didn't.
I have my
different
little cheat sheet here.
Okay. That's a unit of measurement, obviously, but a millitorr.
Yeah, so 1 millitorr is about 1/1,000,000th of an atmosphere.
1/1,000,000th of an atmosphere.
Yes.
Pressure. So this is, okay, got it. Check that out. We learned something else. You all are blowing my mind right now. So I want to get to the fact. Can we see well, Joni? Joni, we're good? Okay. So now back to the jiggling of the particles all around. All right. So what's happening here is that, okay, there's a lot of different things, and I want you to be able to explain how fusion takes place in this. That's where I want to get to. We know heat is like the movement of atoms around in some respects, and then like this is the movement of particles, but it's not fusion. It's not creating fusion.
No.
Can you take us from what's the difference between the particles moving around here and the particles that eventually cause fusion?
Sure.
Okay.
So as Audrey mentioned, the temperatures in this, at least the electron temperatures, she said 11,000 degrees Kelvin, which in Fahrenheit is 10,000 degrees-ish? 20,000 degrees Fahrenheit. So that sounds really, really hot, 20,000 degrees. But for the nuclei that we're interested in to fuse, that's actually way, way, way too cold.
Okay.
And so in an actual reactor, if you want to create fusion, you need temperatures exceeding over 100 million degrees Celsius or Fahrenheit. At that point, it really doesn't matter. It's just very, very hot. And so in this case, we just don't have the temperatures that you need to actually create this fusion process.
Okay.
But in an actual reactor with really strong magnetic fields, with really powerful antennas to send radio waves in, you can get those temperatures in the plasma such that fusion can actually have a chance to occur.
And so fusion, we're going to give the definition. I've tried to explain this on chat. We've done this very well. But fusion is they're moving around so fast and with so much energy that they collide at certain. Go ahead and break it down. I'm not going to do it again. I already did it. Check the VOD. But I want to hear the experts. Like the fusion.
They have enough energy such that they can basically overcome the repulsion that particles may have to getting close together, such that they can form a composite atom or nucleus.
Right, okay. So the difference between this and getting it to where we want it to be, because you all are obviously manipulating the plasma. You've shown how magnetism, so you need to increase the power, increase the magnetism to be able to harness much higher orders of magnitude of energy.
So when plasmas are really, really hot, like you'd find in an actual reactor, they become harder to confine. So that's the other thing, is you need to have stronger magnetic fields to actually confine the plasma so they don't hit the walls and melt things and destroy your reactor. Another thing to mention also is that this is just an air plasma. In an actual reactor, we use lighter elements like hydrogen, isotopes of hydrogen, because the energies that you need to fuse lighter elements is a lot lower than really heavy elements.
Got
like,
it.
Nitrogen or argons, which is the case here.
I'm impressed, Audrey, and I'm impressed too that you were part of that group that had this idea. This is pretty neat. This is much different than other maker spaces that I've seen.
Yes.
So, that being said, is there anything else that we can see here while we're here? He's turning it off.
Yeah. Would you like to look at a spectrum of the plasma? So we have a tool here.
What is it?
It's called a spectroscope.
Okay.
And when you look through it, it breaks light down into a rainbow, and you can see what parts of the rainbow are in the light you're looking at.
Oh, wait. So it has the rainbow. I see the rainbow.
Yeah. And because this is purple, you get the more purple part of the rainbow.
I see.
Another fun experiment you can do is you can actually point that at a phone.
A phone?
Yeah.
Now is my phone gonna? Okay, your phone.
So
you can see what type of light.
Yes.
Okay. And it's more blue.
So you should see 3 distinct types of light here.
Okay, I see.
It might be a little too bright in here.
I see blue. I see.
Yep.
Is that like green?
Yep.
And then a little red?
Yeah.
Ah.
So that's the LED pixels.
That's
in your
right. Ah, so I saw the LED pixel, RGB.
Yeah.
All right, cool. And then here I just see a lot purple. This is neat. This is neat. I don't know if you all can see. This won't work on camera, right? Like I can't put that. No. Okay, so you all can see me see it. Well, maybe you can't see me because it's a little dark and I have a nice shade on me. But I promise you, I see it. I see it. This is pretty cool, Audrey. I think this is dope. And this is called a what again?
Spectroscope. You can get
Spectra.
them for like $10 on Amazon if
Okay.
you want to try it out for yourself.
Nice. That's a nice little plug too. Nova, please drop the definition of spectroscope in the chat. All right. Keep your questions coming. I know you're putting questions. I see you. I don't see you, but I'm pretending like I see you because this isn't live. But put your questions in the chat, and hopefully our team can answer it for you. We got another question right for the team? Okay, cool. All right, so maybe we can hit the lights real quick. I have one other question too, because chat, I want to make sure we can connect the amazing research that we're all witnessing right here at the MIT Plasma Science Fusion Center, PSFC, right? Checking out, we learned about the tokamak, the Alcator C-Mod. This is the Alcator that Audrey and other phenomenal grad students here were able to create in this wonderful nuclear makerspace. This is all having to do with like different components and parts of how fusion is made possible. Why is it important? Why is fusion important? What is the whole like reason we're trying to do this? Because a lot of people may have heard a little bit about it here and there. Like ultimately, what's the end game?
So the whole burning dinosaurs thing is getting a little bit old.
Okay. Okay. Gotcha.
We don't want fossil fuels. So this is a lot better for the environment in a lot of ways. It can create power in a steady stream. You can control when you turn it on and when you turn it off. Not this device, obviously, but a real fusion reactor.
I saw. Matter of fact, maybe we can go check it out. I saw that you all had this diorama over in the hallway.
Let's go take a look.
Okay, we can continue to break it down there.
Yes, but we should turn off the device
Okay,
before
let's
we
turn
leave.
off the Alcator before we say goodbye. Chat, that was pretty dope. I wish you all could have seen through the thing with me there. It was pretty nice, and this is amazing. So when you talk about building stuff, they're actually building stuff here, not just in the long term of research, but students were able to make their own little tabletop plasma donut container. And I'm using donut because it at least gives me the image. And as you can see, the Alcator, it's amazing. It's pretty dope. Will, what are you trying to work on for your particular like PhD though?
It's very similar to the system that we have here. It's very similar to the system that we have here. So you're using radio frequency waves and sending them into the plasma, and in a real reactor, you have a very scaled up version of that.
Yeah.
And so in order to pump in that amount of power into your antennas, you need a big version of this.
Right.
And the research that I'm currently focused on is how do we get a really big version of this, the generator of those waves, to be energy efficient. Because if your reactor creates 100 megawatts of energy, but it takes 90 megawatts to
Right.
heat
It's
it
not
up.
very efficient.
Exactly.
Yeah. Okay.
So there's a lot of inefficiencies in a tokamak reactor, and making your RF power more efficient is just one of those ways to raise the efficiency of your reactor.
Got you. Audrey, I'm gonna go ahead and walk over to the diorama, but can you tell chat, I guess specifically what your dissertation research is gonna be about?
Yes,
as we head over?
so I am working on confining the plasmas. We talked about how in both of the experiments we saw today that the glass is what is holding the plasma in place. Here we are, or in a fusion reactor, we're using magnets like we saw in the linear demo. And I am studying the confinement properties of the plasma. So we want to be able to predict how fast particles and how fast energy leaves the plasma. And so to see whether we actually will get to hot enough temperatures to make fusion work.
Got it.
So that is my research.
Awesome. I'm gonna hit this here because when I was asking you about the purpose of fusion, and I want you to go pick that up again. I just remember when I walked past this earlier, and I saw that the light comes on and everything. This appears to be some sort of like model
Yes.
or demonstration, right?
So yes, this is a demonstration our lab ordered right before the pandemic. It came right after the pandemic, and everyone was very confused because they didn't remember ordering it. But yep, it's working.
Oh, it's working. Okay.
So you push the button and the light turns on, and then we have our image of a plasma here. So we have this purple light that is glowing in the tokamak. You can see the magnetic coils around the outside of the tokamak. The blue area is the blanket, so that's what absorbs the neutrons that are produced by the plasma. And the yellow X's you see are called diverters, and that's how we get rid of heat from the plasma. So once the blanket warms up, you can see this tank glowing blue now. I'm not sure whether you can see it on
Chat,
camera.
you see the
but-
blue and the difference between the blue and the purple there?
And then the blue hot liquid can flow outward to our heat exchanger, which creates energy. And then,
There we go, power.
like every power, for a very long time before we had other types of systems, is
Right.
the turbine.
Turbine, and now we can power up the whole
and
city.
now our city is glowing.
Okay, I got it. So fusion is basically a cleaner, efficient way, if we achieve what we're aiming for, to basically reinvent the power plant.
Yeah,
All
exactly.
right, so this is like the power plant.
We're taking the coal power plant,
Uh-huh.
pulling it out, and dropping a fusion
Dropping a
reactor.
fusion reactor in there. All right, cool. And with it, I guess tokamak has been the term, but what we call these new versions that I guess we're looking at? Is there a name for it?
Yeah, so there are
equivalent to
different types of devices you
Okay.
can use to actually get a fusion
Right,
reactor.
right.
So this is a fusion reactor. The type is a tokamak, but there's also other ideas people
Okay.
have for how.
So this is a tokamak
Yes.
model. Okay. I love it. And we can all see how it works. We can see how we can all get power from fusion. I remember at one point in time, it really, whenever I heard fusion, people would speak as if it was like, this was like science fiction. Like it was like way in the future. Yeah, that would be nice, but let's be real. It sort of feels like the work you all are doing here brings that a lot closer to reality.
That's the hope.
Okay. But I mean, like, can you talk a little bit about how you feel, you all are sort of moving us forward to this being a reality?
Yeah, so we are currently working on building devices that are trying to prove all the ideas that we've had about how you could actually turn this into a reactor. And once we prove those ideas experimentally, we can start building the actual reactor.
It's pretty cool.
Yeah, do you want to go check out some of the work we're doing at building a fusion reactor?
Sure, yeah, we can go back. Is that back in the design center?
Yeah.
Okay, cool. Alcator. How can I get one of the Alcator shirts? Are they available online? Like, what's the link?
Juliana might have a couple ones.
Hey,
for you.
Juliana. Juliana, we'll be talking to Juliana very soon. All right. But while we're still streaming, this is a nice little model here, huh?
Yeah, so this is a tokamak model that was built by an undergraduate student at MIT.
Mm-hmm.
And this shows all of the different types of magnetic fields that you have going into a tokamak. So this is the central solenoid coil we pointed to before. These are the big, beefy toroidal field coils.
Yeah.
And then these are the poloidal field coils that stabilize the plasma from moving up and down.
Chat, I feel like this would be a really good building stream, right? Like, Joni, we could get a stream where I can build my own little mini tokamak.
We do have a project where we build our own tokamaks out of Legos. That's
Really?
one of our activities.
Chat, we might
Do you
need to do
visit
that.
the
We
lab?
might need to do that. As a matter of fact, I don't know if you all know this. Chat, you all know this, but we are building our own engineering escape room. In one of our days, we're going to be focusing on energy and the environment, right? So we're going to bring a little bit of, elements of fusion in there so we can make sure that the players and participants are able to demonstrate some sort of knowledge of it. But I actually think that this gives us a really good picture of how that particular puzzle or that set could even look, right? Because obviously this is pretty small, and in real life, you're not going to get inside of a fusion reactor or anything like that.
No.
But nevertheless, it's really cool to see how it's all shaped and then kind of has this inner diameter and this outer diameter and all these coils. That's pretty neat. We're going to work on that. We're going to try to implement that into our escape room.
Yeah, I've been out working fusion reactors, and you actually can't even get into the same room
Wow.
as the fusion reactor while it's going, or you will die.
Yeah. We don't want. Yes.
There's a whole sequence of processes to make sure that everyone gets out of the room before any experiment starts. And there are buttons everywhere and a countdown. It's very fun.
Actually, can you describe that sequence a little bit? That might be helpful for this game.
The sequence?
Yeah, so I think it works a little bit differently at different reactors. I was at a reactor in Germany called Azdex Upgrade for a summer, and the process of that is that you start a shot sequence, so you have a science coordinator and an operator. So there are two people who are running the device. They start a sequence, and then there's a certain amount of time between each of the experiments, and people can run into the experimental hall to make changes to the experiment in the middle.
Yeah.
And then they have to run out, and they have to make sure that there's no one in the room, there's cameras, there's a labyrinth, there's emergency panic buttons,
Yeah.
and then it counts down. I think it's a 60-second countdown that plays in the room,
Yeah.
and then you can get out.
We shout out to Trapology. Shout out to our friends at Trapology Boston. Shout out to chat. We're gonna have to keep that in mind next time we brainstorm. I like that, Audrey. Thanks for sharing that with me. Yeah. So this is pretty cool. I'm seeing a lot of other pieces over here behind you. These are just little components.
Yeah, so this is all about our magnets. So you can see all the different magnets here, how important they are to creating the reactor. And we saw that they take a lot of energy. But we actually use superconductors, which don't take any energy, or very, very little energy.
This is like a little metal tape kind of thing,
Yes.
right?
So,
Okay.
yep, this is rare earth barium copper oxide tape.
And this is superconducting. It can take high temperatures.
High temperatures being liquid nitrogen.
Oh, okay, okay.
It's not superconducting as it's sitting there.
Okay, okay. And then what is the other thing? I've seen the acronym HTS. Is that basically high
High temperature superconductor.
superconductor? There
got
we
it.
go. Boom. HTS. Get you some HTS if you want to do some of this research. Now this is pretty neat. This is pretty neat. This is just extra hanging around.
Yeah.
Can I take this to my microspace back at the? No, I won't. We'll work that out offline. But all right, cool. This is really neat. I saw this too right here. Shout out to your lab manager. I don't know where he is, but he dropped off some pretty cool. He said it was candy, but I look at it and it says toxic waste. Chat. The lab manager or somebody who works in the lab bought some sour toxic waste candy. I might try it before we get off stream. But what else do we have? What else do we have?
So we have some other types of superconducting magnets and the development of them here. One big development was this casing, which is, this is made of copper, and it's really cool if you take a piece of copper with the holes drilled out of it like this and twist it evenly, it turns into exactly this even design here, and then you can put the HTS strips along here and make structures out of it. And this is a lot of work one of our professors did in making this happen.
Nice, nice, nice. Now I gotta come over here a little bit. Shout out to Johnny behind the camera again. I was told that there is some top secret stuff happening over to my right, so I'm just gonna come over so we don't get in any trouble with no clearance. You all gotta get into plasma research and nuclear research if you want to see some of the stuff that we can't let you see right now. But let me ask our guests before we let them go really quick. What is sort of the big aspirational motivation you all have for why you're even involved in this? What can you share with chat as it relates to like the bigger why that drives you towards this type of research?
Yeah,
Both of you can answer. Yeah.
I really like physics. I've always liked physics, or since I was in high school at least. And I realized that this is a way I can do physics and help the world and try to mitigate climate change, energy stability. Yeah, so that's why I went into it.
I'm gonna get Will over here really quick. Come over here
Sure,
real quick, Will. We don't want to get
Um,
too far over. Yeah.
Very similar to Audrey, I study physics in my undergrad, and it's something that I really enjoy doing. And I also believe that nuclear fusion is a great answer to humanity's problems with climate change and fossil fuels. And it's a really, really difficult project, and
Yeah.
those really difficult projects are going to be the most fun because there's so much to work on.
Absolutely.
And this is just a great example of a really difficult problem that if we figure it out and if we solve it, can change the world.
Yes, I love it. I love it. Well, chat, y'all gotta show them some love. They said it's a very hard problem. I believe it, just based on what I've seen today. But we can't run from difficult problems. That's what we don't do here on Nova Building Stuff, because a lot of times the bigger the challenge, the bigger the opportunity. And I think fusion is a massive opportunity, not just for you all in your academic careers, right, but for humanity. So shout out to them to show them some love. Let's give them a hand clap. I see everybody drop the emotes, put the love down there. And on our way out, I just want to remind you all that we're going to continue the fun right here on Building Stuff with Nova. Right now on the screen, you probably can see, hint, hint, the program schedule for next week. We're not going to be streaming on Monday and Tuesday because, truth be told, I need a little break, all right? But after the break, we're going to be back on Wednesday for another great stream. So until next time, I hope you all enjoy and keep building. Peace. Sour. Toxic waste. Nuclear fusion. Okay. All right.
What flavor did you get me?
I got the pineapple passion. Plasma. All right. See y'all later, chat. Thanks for hanging out with us right here on Nova Building Stuff. By the way, hit follow if you haven't already. And just keep rooting for them. Fusion.